What if I told you that you could have a kind of superpower? The ability to see this entire world of heat that's completely invisible to our eyes. Well, that's exactly what thermal drones give us. They let us see the secrets hidden in plain sight. And in this explainer, we're going to break down exactly how it all works. But here's the big question, right? When you see one of those cool-looking thermal images, with a glowing hotspot on the screen, can you actually trust it? Is that a critical failure about to happen, or is it just a trick of the light? Or, well, a trick of the heat? And that, right there, is what this is all about. The difference between a pretty picture and legally defensible, truly actionable data. It all comes down to one single thing: a strict, repeatable procedure. It's the hard science that backs up the superpower. So to really see how this plays out, let's follow Jane. She's a level 2 certified thermographer, a real expert. And she's on a mission: find a hidden roof leak in a massive commercial building. We're talking about a problem that's totally invisible from the ground, but could be absolutely catastrophic. And believe me, the stakes here are huge. This isn't just about a small drip in a bucket. We are talking about hidden moisture that can rot out the building's core structure, leading to millions in repairs and, you guessed it, a massive fight with the insurance company. So Jane's data, it has to be perfect. No room for error. This is exactly why Jane's work doesn't start when the drone's propellers begin to spin. Nope. It starts hours, sometimes even days before, with some incredibly careful planning. This is where the foundation for data you can trust is actually built. And the whole thing really hinges on this one key scientific principle: thermal inertia. Okay, think of it like this. On a hot, sunny day, the entire roof just soaks up the sun's energy. But after the sun goes down, the dry parts of that roof cool off really fast, while the hidden, waterlogged insulation, it holds on to that heat for much, much longer. And that temperature difference is the glowing breadcrumb trail Jane is looking for. So this means the environment has to be just right, which brings us to Jane's pre-flight checklist. Is the wind under 15 miles an hour? Any more than that, and it'll literally blow the heat signature right off the roof. Is the roof surface completely bone dry? Because even a little bit of dew can cause what's called evaporative cooling and create totally false readings. It has to be a go on every single one of these points. And this brings us to timing, which is, and I mean this, everything. The mission can only happen in this very specific slice of time. At sunset, the sun stops heating the roof. About an hour later, the cooling really kicks in, and for the next few hours, that thermal contrast, the difference between wet and dry, it just gets clearer and clearer until it hits its peak. That is Jane's window of opportunity. Okay, so Jane's confirmed the conditions are perfect. She's on site now, but that drone, it's still on the ground. Because before it ever takes off, she has to perform this on-site ritual, a series of calibrations to tell her camera exactly how to interpret the world accurately. First step, she's got to account for reflections. You see, everything reflects thermal energy, even the cold, clear night sky. So to measure this, Jane uses this simple but honestly brilliant technique. She puts down a piece of crumpled aluminum foil. It acts like a perfect little thermal reflector. When she measures its temperature, she's actually measuring the reflected apparent temperature, or RAT, coming from the sky. It's a critical value she needs to get this right. And here's another pro move that might seem a little weird. Jane actually sets her camera's emissivity setting to 1.0. Now, why would she do that? Well, it forces the camera to record the pure, raw, uncorrected thermal energy that's hitting the sensor. It stops the camera from making any guesses on its own, which preserves the integrity of that data for precise adjustments later on. Now we get to what is arguably the most critical step of all. Just one blurry thermal image, one single out-of-focus shot can throw off a temperature reading by more than 20 degrees Celsius. That is a massive error. It's the difference between finding a catastrophic leak and missing it completely. So Jane leaves nothing to chance. She sends the drone up to the survey altitude, manually focuses the lens until it's perfectly tack sharp, and then she locks it. She also locks the temperature range, the span, so that every single image she takes from that point on is directly comparable to the last. No autofocus, no auto anything, just pure, consistent, reliable data. All right, with all that prep work done, it's finally time. The drone lifts off. And this isn't some joyride. It's executing a pre-programmed, fully automated flight plan, making sure it gets total coverage of the entire roof with scientific precision. And as it flies, it's not just capturing one stream of data. It's grabbing 3 at the same time. You've got the radiometric JPEGs, where every single pixel has a temperature measurement baked in. Then you have a regular high-res photo for visual context. And finally, you have all the metadata: GPS location, altitude, and every single one of those camera settings Jane just dialed in. And then, suddenly, she sees it on her monitor, a glowing hotspot, exactly what she was hoping to find. But she doesn't just mark it and let the drone continue. Nope. She pauses the automated flight, takes manual control, and flies a tight circle around that spot. She's looking at it from every angle to confirm it's a real issue under the surface and not just a reflection from a metal vent or a small puddle. So, the drone has landed, the batteries are cooling off, but this mission is far from over. Now comes the final, and maybe the most crucial phase: turning those thousands of pictures of raw data into irrefutable proof that the building owner can take to the bank. And to meet industry standards, especially for something as critical as a multi-million-dollar roof, Jane schedules a second flight within 48 hours. Why? To prove the anomaly is persistent, that it wasn't just some weird one-off event. If that spot shows up again under the same exact conditions, her confidence in the finding just skyrockets. And all of this data, every single step we just walked through, it all gets documented in a standardized report. You can see it here. It shows the wind speed was compliant. It shows the reflected temperature she measured with the foil. And look at this. The temperature difference of the anomaly was a massive 14.1 degrees Celsius warmer than a similar dry area. And because Jane followed that procedure to the letter, she can label this a high-confidence finding. And she can use that key phrasing, definitive finding. The temperature difference is huge, all the metadata lines up, and that second scan proved it was persistent. This is the kind of language that gets results. But what if the data wasn't quite so perfect? Let's say the temperature difference was significant, but the shape of it was a little strange. Well, then she'd classify it as medium confidence. And notice how the language changes to suggestive but not conclusive. It flags a potential problem, but rightly calls for more investigation, like taking a core sample, to be absolutely sure. And finally, what if the data was captured in windy conditions, or maybe some critical metadata was missing? That gets a low confidence rating. This is the thermographer's way of saying, look, you cannot trust this data. It protects everyone involved from making a very costly decision based on what could just be a thermal illusion. So in the end, you see, this rigorous procedure, it does so much more than just to find a problem. It creates actionable intelligence. It provides the solid proof needed for insurance claims. It's legally defensible if things get messy. And maybe most importantly, it gives the client priceless peace of mind. Which really leaves us with one last thought. We've all heard that old saying, a picture is worth 1,000 words. But after seeing all the science, the procedure, and the proof that goes into making one, what do you think a radiometrically proven thermal image is really worth?